Now that we've talked about the chain rule, we're going to extend the chain rule into allowing us to find the derivative of variables that aren't necessarily with respect to what we're differentiating to. For instance, if I'm taking the derivative with respect to x and I want to find the derivative of a function of y, how I would go about doing that. Now, up to this point, all the equations that we have worked with have been explicit functions, meaning they have been written as y equals, and all of the input variables have been on the other side. So it's been real easy to take the derivative of functions when they're written that way. However, we're going to look at the process of implicit differentiation, which means that I could have an equation of mixed variables, and I'm going to have to learn how to take the derivative of this expression where I have more than one variable on a side and to write it correctly. And the process of implicit differentiation just builds on the chain rule, as I said before, where if I'm taking the derivative with respect to x, some function of u, so f of u, what I would first do is take the derivative of the outer function with respect to the inside, so df over du times the derivative of the inner function, which would be the derivative of u with respect to x. So notice if you multiply those two together, the du's would cancel and I'd have the derivative of f with respect to x. Now, if I extend that to say, all right, well, how would I take the derivative with respect of y? Well, we think of y as a function of x, and just temporarily we'll look at this as the derivative with respect of y of x. Now I can see that I have the chain rule, where I would first take the derivative of y with respect to x, dy over dx, multiply that by the derivative of the inner function of x, which would be the derivative of x with respect to x. Now, you get to say that the dx's would cancel and leave me with dy over dx. And we'll see that as we work our way through these problems, that as when I encounter a variable that I'm not taking the derivative with respect to, we'll have to write the derivative of whatever that variable is with respect to what I'm differentiating with respect to. So let's look at this first one. Let's take the derivative of y with respect to x of x to the third power. Well, I don't necessarily have an equation here. Basically, this is just saying what's the derivative with respect to x of x to the third, which would be 3x squared times the derivative of x with respect to x. Well, we don't write the dx over dx part. And we're used to saying that as being 3x squared. Now let's look at that slightly different and say, all right, well, let's take the derivative of y with respect to x of y to the third power. So I'd first do the derivative of the outer function, which would make 3y squared. Now I'd have to do the derivative of y with respect to x, dy over dx. So the derivative of the outer, which is the third power, times the derivative of the inner with respect to x. That's where the dy over dx comes into play. Now, what if we have the product, x times y, we want to take the derivative of? Well, you would do the product rule here. First times the derivative of the second, dy over dx, plus second times the derivative of the first, which would just be 1 dx over dx, or just 1. And so all we would have would be x times dy over dx plus y. And here is the derivative with respect to x of this function of multivariable. So I'd proceed, take the derivative of each part separately. And so the derivative of 3x, or x to the third power, would be 3x squared plus the derivative of y squared. So think of that as y to the second power, and I would do my chain rule, which says that I would do the derivative of the outer, so it'd be 2 times y to the 1 power times the derivative of the inside, which would be dy over dx. So I have to do that part anytime I'm taking the derivative of a variable that is not with respect to what I'm differentiating to. And then minus, I have to do 3 times xy here, so that would be 3 times, and then I would do the product rule. First times derivative of the second plus second times derivative of the first. And we've written our derivative line here. Okay, so we've looked at finding the derivative of expressions that have multiple variables in it. And now we're going to apply this to finding the implicit derivative, or actually I take that back. We're going to find the derivative of an equation that has x's and y's in it that's not written explicitly. And we're going to use the technique of implicit differentiation to find the derivative. And I have some steps here. Basically, since we're going to be taking the derivative of an equation, you want to take the derivative of both sides with respect to x in this case. Or these practice examples here, we're going to take the derivative with respect to x. And make sure that you're applying the chain rule at the correct time. So if I'm taking the derivative of the y, I have to rewrite the y derivatives as dy over dx. And then we work and do some algebra techniques to try to get our derivative written as dy over dx equals. So here we have this first example. We want to find the equation of a tangent line to the curve at the point that's given. And so what we need to know is, since we have the point, we have the x value and the y value, is we need to know what the slope of the tangent line is going to be, which means that we need to take the derivative of both sides of our equation. So I need to take the derivative with respect to x of x to the third plus y to the third, and take the derivative with respect to x of 6xy. And so the derivative of the left-hand side is going to be 3x squared plus the derivative of y to the third power would be 3y squared times dy over dx. And then I do the same thing on the right-hand side. Well, we have to do the product rule because we have x times y. And so it would be first 6x times the derivative of the second, which would be dy over dx, plus second times the derivative of the first. Well, the derivative of 6x is just 6. And then we work to simplify. We want to get all of the dy over dx's on the same side here. So I'm going to put them on the left and move everything else to the right. We'd have 3y squared dy over dx minus 6x dy over dx is equal to 6 times y minus 3x squared. And then factor out the dy over dx. So dy over dx times 3y squared minus 6x is equal to 6y minus 3x squared, and then divide. And so we would divide, and we would have our derivative of y with respect to x is going to equal 6y minus 3x squared over 3y squared minus 6x. So this is the expression that we're going to use to find our slope of our tangent line. So we're going to put in 4/3 for x and 8/3 for y, and we're going to evaluate our derivative. So our derivative here, and we can use some notation, the derivative of y with respect to x, when we put in the coordinate. Now, some people write x equals and y equals, but I'm just going to write it as a coordinate. It means the same thing. So 4/3, comma 8/3 is going to equal, and then put those values in. So we'd have 6 times 8/3 minus 3 times 4/3 squared over 3 times 8/3 squared minus 6 times 4/3. And then we would simplify. All right, so we wind up getting 4/5. That is the slope of our tangent line. So we're going to write our equation of the tangent line. So I'll zoom in here. So we know that the slope of the tangent line is 4 over 5. Okay? And so the tangent line equation is going to be y equals the y value of the point of tangency plus the slope of the tangent line times x minus the x value. All right, this one here is different. Look at the notation. We want to find d squared y over dx squared. That means find the second derivative. So to do this, I'm going to have to first find my first derivative. Well, we're going to take the derivative of both sides of this equation. So I'm going to take the derivative of the left with respect to x. And I'm going to take the derivative of the right-hand side with respect to x. Why with respect to x? Because that's what it tells me down here. Take the derivative with respect to x by having the dx on the bottom. All right, so now we differentiate. The derivative of the left-hand side is going to be 6x squared minus 6y dy over dx is equal to 0. Now, you don't always have to stop and rewrite this as dy over dx equals. You could proceed forward, but for this problem, it's actually going to be easier to isolate the dy over dx. And in doing so, we'd have 6x squared is equal to 6y dy over dx. And I would divide by 6y. And so we would have x squared over y is equal to dy over dx. There's the first derivative. To find the second derivative, we're going to do the derivative of the first derivative. So we need to take the derivative with respect to x of x squared over y. And see, if I do it to the left, I do it to the right. And that's going to give me, my right-hand side would be d squared y over dx squared, which is nothing more than the second derivative of y with respect to x. So we do the quotient rule because of the left-hand side. Quotient rule, bottom times the derivative of the top, which would be 2x, minus top times the derivative of the bottom. Well, the derivative of the bottom is dy over dx, all over bottom squared. So that is my second derivative. Now, notice how we have a bit of an issue here is we have the first derivative notation present in our second derivative. So what you would do in this step is you would substitute in x squared over y for the dy over dx, and you would continue forward. So we'd have 2xy minus, so it would be x squared times x squared over y, so that'd be x to the fourth over y over y squared is equal to my second derivative. And a real easy way to simplify this is to multiply to get rid of the fraction in the numerator. So I'm going to times both the top and the bottom by y, and I'm going to work towards the left because I'm out of room. And we would have our second derivative here. It's going to equal 2xy squared minus x to the fourth over y to the third.